So we'll do a couple of kinetics problems here that we're going to use the normal tangential coordinate system with. And so what we've got here is a wrecking ball. So we've got something that's got circular motion, right? So that again might give us a very good idea to use normal tangential. Right? Anything that's got circular motion is going to work out real well because we've got a radius of curvature. So what we're going to do here is we are asked to find the tension in the cable, right? We're asked to find a force. And so there's some kinematics given to us. But if we want to find a tension, what we need to do is draw our FBD KD for the ball. So we're gonna draw at an orientation theta. So let's do this. Let's draw a free body diagram and a kinetic diagram. So you probably want to stop, pause it, give it a shot, and when you've done that, then you can go ahead and turn it back on. So, all right, my wrecking ball to do a free body diagram, I've got to cut the cord that it's connected to. All right, I've got the mg term as well. All right, I'm going to draw that thing at an angle theta. And over on the other side, this is where our coordinate system comes in. All right, I'm going to define my tangential direction in the direction of the velocity. The normal direction, right, is toward the middle of the circle. So I'm going to go ahead and put that coordinate system right here. There's the tangential. Right, there's the normal direction. So now over on my kinetic diagram, I'm going to have two terms. I'm going to have mass times v squared over rho. And I'm also going to have, that would be obviously in the normal direction. And here I'm going to have mass times AT, right, the tangential acceleration. So there's my FBD KD system. So if we apply our equations of equilibrium and do just a little bit of math, we'll end up with a picture, or excuse me, we'll end up with an equation that we see below. If we sum forces in the normal direction, all right, we will end up avoiding the tangential acceleration, and we have a nice equation for the tension. And again, we're asked to find the tension at a certain instant. All right, we're told the ball has a certain speed when theta equals 0. So that would be our initial. We've got a velocity of 8. So when we go ahead and use, again, theta equals 0, there's a cosine term up there, cosine of theta, which ends up equaling 1. And we can just go ahead and plug in our values that we have, and we would end up finding that the tension in the cable, again, at theta equals 0. Now we'll solve for the angle theta to which the ball swings before it stops. And again, remembering that it's going to stop when the velocity equals 0. The velocity is only going to be in the tangential direction. And again, we just got the fact that the tangential direction moves, or the tangential changes as a function of time. So we've got the acceleration in the tangential direction, which again we would find by summing forces in that direction, is equal to minus g sine theta. And we're interested in finding the location where the velocity equals 0, so where that ball stops moving. So our kinematics, we're going to use the fact that we know the acceleration in the tangential direction. We're going to use a ds is equal to v dv. And we know that the path is related to the radius of the circle times the strike. So as I proceed, I'm just going to go ahead and take my expression for ds, plug it in right over here. I'm going to take my expression for the acceleration, again in the tangential direction. I'm going to take all the constants outside, so I end up with minus gr on the outside. On the inside of the integral, I have sine theta d theta. On the other side, I've got an integral of v dv. So let's kind of make a big deal of our limits of integration. So I know that I'm going to go from theta equals 0 to, again, some theta final that I'm going to find out. I know that my velocity at theta equals 0, which was given to me, goes from 8. And all the way up at this theta final, I'm going to end up with 0. So I can go ahead and integrate this. So I'm going to go back and carry this down, minus GR out in front. I've got minus cosine theta evaluated from theta f to 0. Over on the other side, I have 1/2 v squared evaluated as seen. So if I go ahead and now plug those in, I end up with minus GR minus cosine theta f minus a minus cosine 0 is equal to 1/2 0 minus 8 squared. And so as we just kind of follow that down, we know that cosine of 0, sorry, that's a 0 right there. I know that cosine of 0 is 1. All right, if I play with my signage a little bit, I end up with that equation right there. And so I kind of have the math filled out for you right there. Is that from that point on, we're just going to go ahead and take it all the way down to go an inverse cosine. And so we end up with an answer for theta. So you just have to check the inverse cosine of 0.7282. So we'll do another kinetics problem here. We've got a collar that's attached to a spring, right, that's on a circular hoop. So again, another nice hint that we might want to use normal and tangential coordinates, right? We've got a circular path, right? And so we'll end up setting up our coordinate system here in just a moment. We've got a spring that's attached to it. And again, we know that the only way we can get a force in a spring is if we stretch it. So we can calculate the force in the spring then by using the stiffness of the spring, which is given to us right there in the picture of 2 pounds per foot, times the current length of the spring, which we calculated by geometry right up here using the picture. Right? And we're going to take that current length minus the initial length, and that's going to give us a force in the spring of about 4.392 pounds. So if we go ahead and draw our FBD KD, I'm going to go right to that. The collar, I'm going to put the tangential in the direction of the velocity and the direction of the movement. And again, we're told where the velocity is moving right there in the picture. I'm going to put the normal direction right towards the middle of the circle. So I'm just going to carry that coordinate system over here. There's tangent. There's normal. And so what forces do I have, right, on my free body diagram? I take that thing off the collar. I've got the weight, right, shown as mg. I've got a normal force that is applied to the collar from the path. And I also have a force of the spring. Over on the other side, we'll play with some geometry here in just a minute. Over on the other side, I've got a mass times a tangential acceleration. And I have a mass times a normal acceleration, which I know is going to end up being m v squared over rho. And we're told some more things about the radius of the circular path, which is 3 feet. So what I want to do, though, is highlight some of the geometry in here, right? At the location that it's located, we're told, right in there, you've got 120 degrees. And we've got a triangle sitting right there. And what we're going to be interested in is I'm going to want to know the angle right here, because we're going to have to use equilibrium equations. So I need to know the angle between the normal force and the force of the spring. So if we highlight this, we've got a triangle that has 5.12 length there. It's got 3 and 3. So if I've got an angle theta here, that angle would also have to be theta. So I've got that 2 theta plus 120 has to equal the total inside of 180 degrees. So that would give me that theta is equal to 30 degrees. So I know that that angle right there is 30 degrees. Let's do a couple more here. Looking up here, I know that the angle in the normal direction to horizontal would be 60 degrees. And so if I just complete my triangle, I know that that would be 30 degrees as well. So now I've got all my forces accounted for, all of the geometry that I need to that I'm going to need to use. And so let's apply some equations of equilibrium. Let's sum forces in the tangential direction. And so what do I have? I've got mg cosine of 60 degrees. I've got minus the force of the spring. And then I know if I'm 30 degrees there, that means I'm going to be 60 degrees there. So that's going to be cosine 60 degrees. And that's going to be equal to MAT. So I can go ahead and solve that for the acceleration in the tangential direction. If I go ahead and also now sum my forces in the normal direction, what do I have? I'm going to call positive going towards the middle of the circle. So I'm going to have then minus n. I'm going to have plus. I've got gravity component going in the positive direction. I've got a force in the spring component also going in the positive direction. And then I've got my mass times normal acceleration. And so there's my equation. All right, and I can just go ahead and solve that thing, giving you the math right there. I can solve that for the normal force. Right, I know that the velocity, right, I'm given that the collar speed is 4 feet per second squared. And so that's how I end up with plugging in a 4 right there for the velocity. There's my radius of curvature going to 3. Right, there's my mass, which is my 5 pound divided by 32.2. So I just carry out all the math, and then I find that I've got my normal force that's applied to the collar that I can solve for. If I want the total acceleration, right, my total acceleration is going to be v dot in the tangential direction plus v squared over rho in the normal direction. And if I want the magnitude of that, I'm just going to square those two things. So I can see I'm just going to use my answer for tangential. That'll go ahead and fit right in there. And then I've just got my v squared over rho, which just sits in there. So I end up with a total acceleration of 5.68 feet per second squared on that collar. All right, the last one we'll do is a homework problem that's similar to one you've got on this homework assignment, but it'll show up on a later homework assignment. So if you want to read through that here, we've got a car that's going over the crest of a hill, and you're asked to determine the maximum constant speed at which the car can travel without leaving the surface of the road. We're going to neglect a couple things, and of course the car has a weight. So we've got curvilinear motions and circular, and so I'm going to go ahead and put my tangent in the direction of movement, put my normal right towards the middle of the circle. And so let's draw the free body diagram, the FBD KD, and you kind of see it forming up here. It's actually incomplete. There's a force that's missing on there. So let's just kind of go through that right there. There's my car. So I've got the weight of my car, of course. I've got a normal force the ground applies, right, keeping it on that surface. And I've also got a force of friction that would be there. Right? It doesn't say the wheels are slipping. So I have this force of static friction, which again, I need to think of that as I am going to be able to calculate it. I know it has a maximum value of mu static times n, but again, the force of friction in a no-slip condition is calculatable. And so over on the right-hand side, what I've got is two accelerations. I've got an acceleration in the normal direction, which is going to be v squared over rho. And I've also got one in the tangential direction, and I can just call it MAT. Now I'm told something about a constant speed. So if v is a constant, that would mean that v dot is equal to 0. So there we go. I know that the tangential acceleration is equal to 0. And now as we look back at the other side of the diagram, we'd be able to solve for the force of friction. It's going to be a function of the weight. All right, well, let's get the car all the way up to the top here, right, just to the top of the crest. And without leaving the surface means that this normal force is going to be approximately equal to 0. It's just going to be a fraction above. So essentially, it's going to be 0 in our calculation here. And again, all the way at the top, we still have 0 tangential acceleration because we've got constant velocity. So it actually comes down to a very simple FBD KD system, right? Just a couple of things that were applied. One was constant speed, and the other, again, is that it just without leaving the surface. So again, that's the case where that normal force is going to be just a fraction above 0. And so I'll sort of stop right here for you, but you'll end up with another homework assignment due on Wednesday where you've got a similar condition. So just kind of remember that. If it's just without leaving, the car doesn't leave, but I want to know the maximum speed that it can occur without leaving. Essentially, that normal force is just going to be equal to 0 in our analysis.